Hello, I'm here representing the challenge area 3, the verification of trustworthy software. I'm from Red Hat, but there are multiple companies and institutions involved in the area. The goal of the challenge area is to use formal methods to improve software. We generally analyze code performance, the actual code of the software, the cryptographic protocols around it, and work in a way that we develop tools that often start as novel ideas in the academia and with an academic prototype, and try to apply those tools in companies and get them to a daily use, showing what they can do and how can they actually improve what's out there. It's a mixture of institutions from both regions, the Estonia and South Moravia. And as I mentioned, usually it's the academia that comes with the ideas and prototypes of the tools, and then the industrial members who apply them. I will do a flagship example on the tool that is called Perun, and then mention several other tools that we have, because going over all of them would be a bit overwhelming at this place within the time frame. So Perun is a modular differential performance analyzer that can reach the kernel. And I'll slightly go into that. It's a performance analyzer, so it helps to identify performance degradations in your software. And it can reach as down deep as the kernel. So you can either profile user space applications, or actually profile just the kernel, or profile both in the full stack. We are actually using it in Red Hat mainly in the kernel part, and much less in the application part, but it can also work in the user space. Now, modular and differential. It's modular in a way that there are different options for the actual performance tool. You can use perf, you can use system tab, instrumentation, whatever fits you, you can plug into Perun. And it's differential because it connects to version control. So you have multiple Git versions of the same software, and you're running performance profiling over the different versions and comparing those to be able to find the performance degradation. So ideally, with the Git information, so it's kind of white box profiling, you can say, oh, there's degradation, and it's this commit within this function, within this line, because you can do it differentially. In reality, it also, apart from tons of data, it gives you all sorts of visualization. This is a flame graph of calls in the kernel, and in the lower side, you can see a differential flame graph of which parts were called more and which parts were called less, so that it helps you to dive much faster into places that changed and changed in either positive or negative directions. So this is a tool that moved from academic prototype to the actual industrial use, because now for about half a year, this is actually running daily at Red Hat within the CI/CD pipeline of the kernel QE team, and they are literally saving man hours, ones to tens of man hours per individual performance degradations, because sometimes it would take 2 days for the kernel QE team just to find out the problem, and now with Perun they can do it much faster. We have a bunch of other tools where we want to go the same flow of getting it actually applied and saving time, or others. This is the Perun. There's also a demo that you can check and try to solve perf challenges with Perun. There's also diffcamp, which is a tool for checking semantic equivalence of C code and potentially a very complex C code. Think like you have a C project, again, we are using it on the kernel, and you want to ensure the stability of the API. So you're checking whether commits that were marked as refactoring are actually only doing refactoring, and there's no semantic change within the code. And we can do that by formal analysis. So it's actually sane and correct, and when it says that there's no semantic change, we can prove that there is none. And if there is one, we can point you to, oh, the semantic change is there, so you accidentally also changed something that you didn't intend to. The third tool that I'll mention is Symbiotic, which is a verification tool, again, mostly for C code, which combines multiple theoretical methods: static analysis, instrumentation, program slicing, symbolic execution. For those of you who know the software verification competition, it's a multi-year winner in multiple categories of the verification tooling. Lastly, it's a project called GobPy within the Goblin project that automatically verifies software and focuses primarily on data races. Now, if you want to take a picture of any slide, this is the slide with all the links. And this concludes the short introduction into the tools that we do in Challenge Area 3. So if there are any questions, they can be either now or feel free to grab me later on here in this space.